In this episode, we are going to focus on the reactions of alkenes as a branch of organic chemistry, and we shall specifically look at the electrophilic addition reactions of the alkenes. And the key reagents that we shall be focusing on will be hydrogen. Hydrogen combines to give us alkenes. Then we shall come to see addition of halogens. Addition of halogens to give us the dihalo alkenes. Then we shall come and see the addition of hydrogen halides to give us haloalkenes. And lastly, we shall see the addition of concentrated sulfuric acid, which gives us the alkyl hydrogen sulfate. Now, in these reactions of the addition reactions, we shall focus on the pathway that is used as we do the addition reactions, which involves addition via Markovnikovs, addition via the anti-Markovnikovs. So someone should have that knowledge as some background to help us see the reaction pathways. So we shall see addition via the Markovnikovs, and then addition via the anti-Markovnikovs. What does Markovnikovs tell us? Markovnikovs tells us that in these unsaturated hydrocarbons or compounds, for example alkenes, addition takes place in such a way that when the hydrogen comes to be added to the unsaturated compound, it adds itself on that position of the double bond to the carbon atom that is carrying the maximum number of hydrogen atoms. Then the anti-Markovnikovs gives us the opposite of that. What does it exactly mean? Take an example. We have, consider this alkene. That is what we have. And now, the key position where we shall see the addition take place is this one. Now, how do we add according to Markovnikovs? This carbon atom has one hydrogen. This carbon atom has two what? Hydrogens. So as we bring the hydrogen atom to be added, it first adds itself this side of the carbon atom that has the maximum number, because if you compare 2 with the 1, the 2 is maximum or is greater than what? The 1 that is this side. That is, for example, if you bring hydrogen attached to another atom X, if the interaction takes place, it means that this hydrogen, as it adds, it will come to this position, not coming this side. And as the addition takes place, we come up with the what? With the carbonium ion. We shall see this when it comes to the what? The mechanism of all these reactions as we go along. Now, the anti-Markovnikovs is specifically the free radical addition, which focuses on only one key reagent, as we shall discuss. That is the hydrogen bromide. Now let us go through the examples and see. We shall begin with the addition of hydrogen to form alkenes. The example we shall use propene to add the hydrogen. And addition, we are saying we are adding hydrogen, but the addition takes place in the presence of a catalyst. For example, common catalyst used is nickel. When nickel comes, it always first sets the addition at 150 degrees. However, still you can have other catalysts, for example, platinum and palladium, which adds the hydrogen at room temperature. Now, I always prefer students first outlining the mechanism to see what exactly takes place. They arrive at the final answer, then you come and write it there. So we come and see what the mechanism spells out. So the mechanism will be, we bring our reactant, the propene, which is this. Then the approach of this hydrogen molecule initiates the reaction. However, a student must remember that this hydrogen molecule exists with a partial positive side and a partial negative side. Then the approach starts in a way that the pi bond interacts with this partial positive side, and we undergo complete cleavage, whereby the electrons in this bond are taken away by the other hydrogen to form a hydride. So what does this give us? It gives us something that is a carbonium ion. But recall what we have just demonstrated here in our addition, that as I bring this hydrogen, the addition to either of these two favors this one that has the maximum number of hydrogen in comparison to this one. So our addition is going to move from this and we add it to that. And if we add it to this, it means we shall have 3 hydrogens attached to this as we create a carbonium ion at that position. So we come and see CH3 carbon hydrogen. Then we have added another hydrogen on this one. Therefore, this one is a 3 as we create a carbonium ion. That is a positive species. Plus, what is the fate of this? It is coming up with a hydride. Next step, the negative interacts with the positive. So this will come and interact with that. And then we come up with our final product, which is CH3, CH2, and then CH3. If you look at this, is an alkane. So someone, after getting this, can perfectly bring it here as CH3, CH2, CH3 as our what? As our answer. What do we see with this? We have added, and we have not lost anything. That's what defines that what? That reaction. So this is the example 1 in what we have seen. Then we bring example 2. Example 2, we create a branched unsaturated hydrocarbon, which is 3-methyl butane. When it interacts with hydrogen in presence of nickel at 150 degrees. This one is just a catalyst, not participate anywhere in what we are seeing as the reaction, but it favors the combination of the reactants. So from this, let us first undergo through the mechanism for someone to know what exactly comes out. In the mechanism, we call what initiates the reaction. First outline our reactant. CH3, CH3, CH double bond, and then CH what? CH2. Recall we will say this is the 3-methyl butane. So initiation of the reaction comes by the approach of that hydrogen molecule towards this double bond. But I will say this one exists with a partial positive side and a partial negative side. So what is the first step that takes place? The pi bond interacts with this partial positive side, has complete cleavage takes place, and we lose. These electrons go along with that hydrogen, form a hydride. What do we come up with? Come up with a species that is a carbonium ion, but of this type. CH3, CH. Where is this hydrogen going to add? Recall what Markovnikov has told us. We are seeing this side has 1 hydrogen, this side has 2 hydrogens. So the maximum side, the side with the maximum number of hydrogens, takes up that what? Hydrogen. So we shall see this one remains the way it is, and we see this one as that plus a positive that gives us, so that defines the carbonium ion form. The fate of this is the formation of the what? The hydrogen. Now this is the tricky part, which I want everyone to be keen as you interact this negative with the what? With the positive. The key thing is, when you look through this species here, it has formed a secondary carbonium ion, but there is a possibility of it giving us a tertiary carbonium ion. Why? When I look at this carbon, it has attachment of carbon this side, attachment of carbon down, and attachment of carbon the other side. So it means we can have a hydride shift or rearrangement, whereby this hydrogen moves from here, it comes this side, as that positive side comes there. So this one means we must undergo rearrangement. And the rearrangement, I will say, it is the same as saying we are having a hydride what? A hydride shift. Why are we saying hydride shift? Yet we already have this. The chemistry behind what we are dealing with tells us that if there is a possibility of a tertiary carbonium ion, we go with that, because tertiary carbonium ions are much more stable than the secondary what? Carbonium ion. So the rearrangement must be sealed, and we come up with the tertiary carbonium ion, and then we proceed with the what? The final what? Reaction. So this gives us CH3, C, a positive. We have our methyl group attachment. Then CH2, because this hydrogen has moved from here and has gone there. Then we have CH what? CH3. Recall, we have our hydrogen which we must bring. And at last, of course, this one must come and interact with what? With that. We can trace our arrow from here. It comes, interacts with that. And the interaction takes place. It means we shall have CH3, CH, and CH3, CH2, and at last CH what? 3. And that is what we come up with. So from this, someone can be able to write the final product of what we come up with here. We have only added and we have not lost any molecule from what we have done. That is for addition of hydrogen. You can phrase various alkenes and try out what is here. Let us go the addition of the what? The halogens. We shall examples and see. We have still, we can bring propene, which is this, and the propene comes undergo reaction with the bromine, but in the presence of an organic solvent. This is an inert organic solvent. Will not participate anyway in our reaction. So let us go through the mechanism before we outline the product that we are saying. But recall still, we will say halogens interact with the alkenes to give us dihaloalkenes. Okay, why is it that we are saying di? Because the two halogen atoms will be added. So let's go through the mechanism and see. The mechanism gives us, we introduce the reactant, which is the alkene, and that is it. The bromine molecule comes. But this bromine molecule exists with a partial positive side and a partial negative what? Side. So the approach of the bromine molecule to the functional group initiates whatever we are seeing here as the partial positive, partial negative. So the next step is the interaction of the pi bond with this partial positive side. And at the same time, complete cleavage of that bond takes place. And all the 2 electrons that are here are given to that bromine to give us a bromine. So we come up with, how shall we add up? We still borrow some Markovnikovs here. This bromine is not going to be added here, but instead it will be first added the other side. This side which has the maximum number of hydrogen atoms attached to the carbon that is carrying the functional what? Group. So what do we come up with? We come up with the CH3, CH2, bromine. But we said as we form this, the carbonium ion also comes into play, plus the bromide what? Ion. What's the next interaction? The positive will come and interact with the what? The negative part. And last we come up with the product with the bromine attachment of that, CH2, and then bromine. This is our product that we get. If someone can keenly see, we have 2 atoms of the bromine, those are 2 halogens. That's why we say dihalo. But as we name, of course we follow the rules of naming. But if you go through those rules, this will be 1, 2, di-bromopropane. This is a vicinal what? Dihalide. We come and put it here. That's our answer. CH3, CH2, CH, 2 bromine. This one, then we come to bring CH2, and then what? Bromine. Let us see. Example, we shall still pick the same example we have used in hydrogen. We come and see a substituent where we have a methyl group attached. What shall we see? CH, CH2. And then we are bringing bromine in the presence of an organic solvent, which is that. So we come and outline the mechanism. the mechanism for the reaction to give us the pathway. Then you come and outline your answer very well. So the mechanism here starts such a way that we bring the key reactant CH3, CH, double bond, CH2, 3-methyl but1 in. That's what we've named this compound. So we come and we bring the bromine molecule. The bromine molecule approach to the double bond brings the true meaning of how it is existing. Partial positive side and then a partial negative side. So the pi bond interacts with the partial positive side as we undergo complete cleavage, and that bond goes and gives all its 2 electrons to that bromine to give us a bromide the other side. So what is the effect of what we have done here? It gives us CH3 carbon, CH3 hydrogen, CH addition, Markovnikovs. So addition of this will come there. So giving us CH2, then what? Bromine. Where do we position our carbonium ion? It is this carbon that has been deprived of a bond. So it qualifies to come and take up that what? That positive, or the carbonium ion definition. So from this, there is the other side of the bromine that has been what? That has been formed. It has taken away all the 2 electrons that were here to the other side. Now what comes next? Someone still must be keenly look at this. This is the secondary carbonium ion, but there is a possibility of coming up with a tertiary carbonium ion. If you look at the position of this carbon, it is attached to the carbon on the other side, it's attached to the carbon on this side, it is also attached to carbon down. So it means we must undergo what we call the rearrangement. The hydrogen shift must take place, whereby this hydrogen must come this side as this positive comes there to give us the tertiary what? Carbonium ion. So we are having rearrangement or hydrogen shift. And that hydrogen shift generates something of this type. Of course, the positive is there, CH3. These are now 2 at that position. Then we have CH2. Then what? The bromide. Recall, we have our what? Our bromide, originally formed from here. So, at last, we now truly come and interact these 2. This with that. And the interaction between those 2 will give us the compound of this type. CH3. Of course, this bromide has come to that position. So we come and bring bromine, come and bring CH2, and then what? Bromine. And this one gives us our compound or our product that we form when we add hydrogen bromine to that what? To that alkene. 3-methyl but1 what? E. And this is what we get. It qualifies to be our product at that. The rest of those halogens, if you bring chlorine, it will follow the same what? Mechanism. If you bring iodine, it will follow the same what? Mechanism. What I've used here has been on the bromine to give you a picture of what exactly is done. So feel free to try out the same examples. Roman 1 bring propene, then you add chlorine and see what takes place. Then Roman 2 bring still chlorine and add, in presence of an organic solvent, add it to that alkene and see what takes place. Just substitute where there is bromine, you are putting there what? Chlorine. I'm very sure things will be able to come out. The same concept will be for what? For iodine. Now, at last, we want also to see another key thing that we always find interesting about this bromine, as it reacts in presence of other reagents which are not necessarily organic solvents. That will take place. Let us see something that is inorganic. Bromine added, but in the presence of what? Concentrated sodium chloride solution. What takes place? Don't gamble this side with writing the product. First, now go through the mechanism. See what takes place. Define the meaning of whatever is taking place, so that you come up with the final answer and write it with a lot of confidence the other side. So we come and bring here. What takes place initially? The normal way. We come and bring our alkene, which is this. It will interact, first of all, with the bromine molecule. But this bromine molecule, from what we have seen, as it approaches the functional group of the double bond, it initiates the positioning of the partial positive side and the partial negative side. So we shall see the pi bond interacting with the partial positive side as complete cleavage takes place to remove that bromine in form of a bromide. So what do we come up with? Addition of this will follow Markovnikov's such that its addition will go to that carbon atom and not this side. So this side will leave what we call a positive hole that gives us the carbonium ion. So we shall come up with the CH3, CH2, and then the bromine. But recall we have created a what? Carbonium ion. What is the effect of this? It is the formation of the bromide. Now what comes next? In our first example, we saw that this one comes and interacts with this, and we come up with a vicinal dihalide. But now the case is different. Presence of concentrated sodium chloride tells us something. It being inorganic, it can undergo through this. It separates, this separates to give us the sodium ions are present and the chloride ions are also present. Presence of this is always defined to be in excess, such that its excess presence deprives the kernel of this to interact with this. Instead, much of this will take up the position that is supposed to be taken up by the bromine. So what am I meaning in this? That instead of this, we simply now bring these chloride ions are too many, so they will come and interact. They surpass the action of this to interact with the carbonium ion. So we come and interact this with the carbonium ion and come up with our final answer, which is CH3, CH, chlorine, CH2, and then what? And then the bromide. So from this, we have two substituents which are halogens, but they are not the same. This is a bromide, and this is a what? Chloride or chlorobromine, and this side what? Chlorine. And if you go through the nomenclature as we earlier discussed, someone must be able to name this. Taking it in mind that the alphabetical order counts a lot. So someone must focus on that first, then you bring this, then you name the original alkane, which is propane. So in such a case, we shall see bromo at position 1, then chloro at position 2, then we name the final what? The final alkane, which we substituted. Now, thank you for watching. I hope there was something that you learned. So in the next step, or in the next episode, we shall see the reaction of the hydrogen halides with alkenes, and then also we wrap it up with the reaction of the reaction of alkenes with sulfuric acid, which is concentrated. That is for the concept of electrophilic addition reaction. Thank you for